So we move on with the microstructure analysis and multiscale stochastic modeling of steel structures operated in the extreme environment. Please, Level.
Thank you. It's a great pleasure for me to take part in this session and present you some results. Okay. Let me introduce my support group, because not whole results of this group is in this presentation. Most of them is my postgraduate student. He is a doctor after defense. I am from Institute of Physical Engineering Problems of the north of Yakutsk from Russia. I'm also the full member of the Academy of Science of Republic of Sakha-Yakutia. I'm from Yakut Science Center. It is a Moscow Electronic Institute, so 2 people is from here, and Moscow State University is a student. All of them helped me to the experimental work. So, next. So here's the content, if we have time, but we haven't. So I would be very short. So first, I introduce the extreme condition in our region. It's very cold temperature. And then about the material testing at low temperature, not all the material, but it's possible to test all the structures, the whole structures. And we did this. Next, the damage, nucleation, fracture mechanism, revelation in structural materials. It's very important that the structural materials, it's not the model materials, so it's a steel. Then the multiscale damage modeling approach and some trying to scale reduction. It's very popular in the world now. Then some final element modeling or stress strain stated like a standard stochastic modeling, what our approach is here, and some lifetime estimation of structure members. Taking into account the extreme environment, of course. What the Republic Sakha is in Russia, it's very west and north, east and north part. It's on the territory, it's about the 6 France. It's very big. And why it's important for Russia and for the world, because here is my city, of course, it's Yakutsk here, on the Lena River. Because we have many important oil and gas facilities here, and even we already used oil pipeline. It's East Siberia, Pacific Ocean, and then power of Siberia. It's some another natural gas pipeline. And of course, we just start with the railroad. It's going from Nerengri, Tomotu to the river of Lena. It's just across the river to Yakutsk. So it's a very important problem. We have 2 problems. For pipelines, it's a weldment, weld joint, and the another is a railroad with some impact factor, impact toughness, that at low temperature is very low. So what about the material testing at low temperature? So first of all is the research of ductile and to brittle transition in structural BCC steel. There is a tension test, impact toughness, low cycle plasticity, fatigue testing and possibility of material and equipment full-scale test, it's possible in our conditions. Also, it's some theoretical based, I just do it. Our results is concerning the internal friction in BCC steel. We reveal that the activation energy is equal to 0.2 electron volt. So it's not a lattice. It is a dislocation and Fanon mechanism. So it's just determined in our paper 2 years ago, 3 years ago. It's very quick time going, yes. And another result is concerning the impact toughness of locomotive steel steels. It's very low at minus 40 and minus 50 and 60. It's decreased even on minus 30. So it's 3 times, I think. So we can have some impressive image of the boundary between the ductile and brittle fracture to make some scale measurements here. So it's fatigue damage probes that after the fatigue was dynamically fractured at minus 40 Celsius. So we did some fractal analysis and used some scale parameters here. For the weld joint, it's just a tension test, low cycling test specimen. It's like this. It's originally welding, it's arc welding. It's a microstructure, micro hardness distribution. So the next is the theory of dispersed structural damage accumulation. So the important is the varying of source and mechanism of damage and fracture, micro and macroscopic study by experimental testing probe, and damage accumulation regularities identification at different scale. So when we have some multi-scale problems in any structural materials, first of all, we should take some K level that introduce that going to fracture. Maybe it's for nanostructures, maybe it's a nano level. For even the structural materials is dislocation, micro cracks, nanopores. So it illustrates this approach. It's a well-known approach that's used. And here, so from mechanicals continua, that all the researchers use these models. And the heterogeneous approach, some of research use this. But we're going to the multiscale evolution approach that use some different model on the different scales. It's very important that in every scale have some original dependencies. It's not the same. So the damage accumulation concept, it's already used in the previous lecture. So we use the same, but it should be maybe scalar, maybe some tensor, limiter, it introduces it like decrease of deformation density of couplet volume. So we use the effective properties and logistic dependencies introduced, because logistic dependencies it have internal properties to include the many level, previous level, like I don't know. For micro level, it includes sub-micro and nano levels. For macro levels, if it's a macro damage, it includes the micro and nano. It's all the levels into it. So we use some microstructure order parameters here. So for weld microstructure, we reveal some big, not so big. It have microns, several. It's about 20, from 20 to 50 microns, micro cracks. Even in heat affected zone and in weld. For locomotive tear, we have another mechanism of fracture. It's impact and plastic fatigue here. So we use some chemical analysis and epoxy. It's energy EDX-analysis to see some element segregation here. So for locomotive tear, we have some crazed cracks here. So even when was an impact between the rail, sorry, it's in Russian, it's a wheel, it's a tear of wheel, and here's the rails, and here's the distance between the rails. So for final element modeling, we used weld inhomogeneity influenced by the different properties in this case. I used free software of Phoenix and just obtained that the biggest stress is not in the weld. So we should use some another model. The stress concentrated it's near in another area of the probe. Concerning the stochastic modeling of crack growth, so we should establish the law of random or regular distribution of macro defects in material, because any real material has a stochastic nature. If we use determinal model and continuous model, we cannot obtain the real distribution of results, distribution of crack velocity, etc. We should use many thousands of specimens to obtain the experimentally results. But if you are going to modeling, we should use stochastic modeling, not the determined approach like final element modeling and etc. So originally, its model is used Bertrand-Brobeck approach. We have modified it several times, but originally it's like the same as a Bertrand-Brobeck model. It's crack growths, ductile crack growths, threshold opening stress, Hutchison rise Rosen. It's first time then we used a plastic flow, of course. And even the used for hydrogen, because hydrogen have a very great impact to fracture. If on the second planar lecture today we are just listing this. Yes, of course, we use stochastic modeling, and the result of stochastic modeling in weld and the base metal is quite different. So about 100 times more higher velocity of crack in weld joint. So it's quite different from another results. Okay. So about the lifetime estimation, we used another approach. It's the damage accumulation approach here. how we can take into account the ductile to brittle transition here. We use some special damage for impact loading. Here's the fatigue, and here's some of the side wearing. Okay. So we use some diagrams of minimal month temperature, and by our experimental results, we obtain the same curves for impact toughness. So impact toughness according to the month's temperature. It's quite different from another regions. So for extreme climate uncertainty, we have calculated damage for 5 years in different regions. For Yakutia, it's close to 0.7, and in Moscow it's 2 times less. But de facto, the locomotive turret lifetime's extreme condition is 3 times as little. So we can use another approach to take into account the must and other factors here. So with these conclusions, thank you for attention. No questions, because we are going to discussion at the end of session. Thank you.
Thank you.